now we are recording. All of these notes will be posted as well, so we'll be able to review them as well. But apologies for the late turning on of the recording, but we are recording now, so thank you for commenting on that. So with our conversion, why on earth would we ever want to do it? Well, it does have one limitation. So x sub a is generally limited to one reaction. So we don't try to solve a problem in terms of x sub a if we have more than one reaction. So we would only use x sub a as a solution technique if we have one reaction. The reason for that is because if we have more than one reaction, it's very easy to extend the expression for extensive reaction to multiple reactions by summing up over all of the terms, right? This is how we account for multiple reactions if we're using the extent of reaction. The problem is that there is no corresponding extension if we want to use conversion. So there's no equivalent extension for x sub a, right? There's no equivalent way that we can like sum up all of the various terms if we have more than one reaction and we want to write everything in terms of conversion of a. For example, you can think of at least one particular problem, which is what if some of the reactions don't involve a? It may be possible to link them backwards to the a, but it's going to be really nasty to do it. And so when you ask the question, why would I do x sub a? Well, one place where you would not use x sub a as your solution technique would be for a system with more than one reaction. If you have more than one reaction and you need to calculate x sub a, so to calculate x sub a EQ for multiple reactions, the J here is the reaction. So the subscript J is referring to reaction J. So you might have reaction 1, 2, 3, 4, 5, 6, 7, however many reactions that you might have. Every reaction gets its own extent of reaction. If somebody asks you to calculate a conversion of a particular species at equilibrium and there's more than one reaction, then the steps are as follows. You first solve for all of the extensive reactions. So you get squiggle 1, squiggle 2, all the way up to the last squiggle, which is squiggle J. And then you would use this formula that I've got right here, which is n sub a is equal to n sub a 0 plus the stoichiometric coefficient of a in reaction 1 times extent 1 plus the stoichiometric coefficient of a times extent 2 all the way up to the stoichiometric coefficient of a in reaction J times its stoichiometric coefficient. So you figure out what's the outlet molar flow rate of A, right? And that's using this formula. And then if you need to, you would then calculate x sub a by its definition, which is n sub a minus n sub a divided by n sub a 0. So it's sort of a workaround, right? I can't use x sub a EQ directly in the solution for a system with multiple reactions at equilibrium. So I have to go back to my extensive reaction, solve it the way that I normally would with, solving for all of the extensive reaction. And then once I'm all done, I can set up a table, not unlike this one, and solve for all of my outlet molar flow rates and calculate the conversions of my species A based on that stoichiometric table. And so it's kind of a workaround, right? If you have more than one reaction, generally conversion is not a helpful tool in terms of the solution procedure. It's something that we calculate when we're all done. If you happen to have one reaction, then you can solve for it directly. It's sort of up to you. Both approaches will give exactly the same result. So yeah, we've got about 15 minutes, 18 minutes, which is perfect. We are right where I want to be because I want to talk about a couple of MATLAB tricks and tips. This sort of expression right here can be a pain in the neck to work out by hand. And also as an aside, it's really enjoyable to color things like this if you've never tried it, to make these little boxes and get closer and closer and closer. It's really enjoyable. But at any rate, this sort of a form lends itself to MATLAB quite well. This is nice for MATLAB. The reason that it's nice is because you can express a lot of these terms in their vector forms. And MATLAB has a lot of built-in functions that are very, very nice for vector formulations. And I demonstrated a few of those a few days ago with the case of A term. And so today I want to demonstrate some of those terms for the product of A sub I term. So it's an approach that can save you a lot of algebraic headaches. For example, making algebraic mistakes is really easy. Hang on just a second. Don't forget, we're in Studio Winston, so sometimes Winston says he has a problem and I need to investigate. It can be really easy to make algebraic mistakes. You've got a negative sign here, this sign's flipping, this sign is always negative, maybe this number up on the top is always changing, but the number on the bottom is always constant. This number is changing, but this number is not, right? I can certainly understand making some algebraic mistakes on there. Totally normal. You only get through those algebraic mistakes by trying them a few times and finding out that you made them, and then realizing what you need in order to not make those anymore, unless you've got MATLAB. If you've got MATLAB, you can save yourself a lot of the headache of having those algebraic mistakes because MATLAB will essentially do the algebra for you. And so with MATLAB, you never have to worry about how do I actually have the correct form of some massive equation like this, and then did I actually enter it into MATLAB correctly? You can save yourself a lot of those headaches with some of MATLAB's vector tools. Hang on just a second. Be right back. Okay. Let's try and pick up where we left off. MATLAB stuff, tricks and tips. The vector formulations in MATLAB can be really useful for this kind of problem. So let's take, for example, this calculation of the product of A sub I. If I wanted to do that, some of the terms that I would need would be things like the stoichiometric coefficients, right? One way to do this in MATLAB would be to define all of the stoichiometric coefficients separately. So something like this. Another way to do that in MATLAB would be to lump all of these into a single vector. So we could call that vector new, and then we could write it as -3, -1, and 2. So we always enter it in exactly the same way that it would correspond to the species. And so if I wanted these species in here, this would correspond to the form of H2, N2, and NH3. As long as we're consistent with that form, then we're going to have a lot of useful tools that we can use inside MATLAB. So for example, if I wanted to similarly define how many moles of everything are coming in, I would pick the same pattern here and say there's 3, 1, and 0 coming in. And this would have units of moles per second. And it's in the same pattern as this one. And so we would calculate our n sub 0 that way. If we, I'm going to erase these right here. Let's say that we happen to guess a value of squiggle or x, but let's use squiggle because it's a little bit easier to use here. Let's just guess a squiggle is 0.25, right? There's only one of them for this particular problem. We can then calculate n, and this is the clever part of Matlab. We can apply the all of the relationships that we've got in such a way in the Matlab code that they actually look very similar to the reactions, to the equations as we write them. So we would write this as n sub 0 plus the stoichiometric coefficient times our extent of reaction. This is now moles per second, but it's the outlet molar flow rate of everything, right? It's coming out as a vector, and it's coming out in the same pattern that we had up here. So we would expect n to be n sub a, n sub b, and n sub c. Right? We get all three of those all at once, and we don't have to really do any algebra, right? I didn't have to do too much there to calculate that. Similarly, if we wanted the total, or let's say the mass or the mole fractions of each one would be n divided by the sum of n. Right? This should look really similar to the way that we would define a mole fraction, because any y sub I is equal to the moles of I divided by the sum, which is n sub t. N sub I divided by the sum of n sub I. The result that we get here when we use it in this vector formulation is that we have y sub a, y sub b, and y sub c. To the question in chat, you don't need a dot here because squiggle is a scalar, right? There's only one value of squiggle here, so you can multiply a scalar and a vector, and you don't need the dot. And now we would calculate, for example, the left-hand side of equation 2.30. If we wanted the left-hand side of equation 2.30, let's think about what that looks like in the equation. Normally what that looks like is the product of a sub I raised to the stoichiometric coefficients, right? And so what we're after in Matlab is something that looks like the a sub a raised to the stoichiometric coefficient of a times a sub b raised to the stoichiometric coefficient of b times a sub c raised to the stoichiometric coefficient of c, right? We're trying to take that product of each one of those a sub i's. Remember, for our particular example, a sub I is equal to y, but if we wanted to be very, general about it, we could write a is equal to y times p divided by p circle, right? That would be perfectly fine if we wanted to do something like that. Let's move these down a little bit. If we wanted to be really general, we would do something like that. But for our particular problem, we wouldn't do this because oops, I didn't mean to change the color there. These two terms end up going to 1, right? Because p was equal to p circle. But if we wanted to be really general about it, we could do exactly this. And we'll just note that a sub I is equal to yi p over p circle, but p is equal to p circle, right? Because we were doing everything at atmospheric pressure. So it just ends up looking like a is equal to y. So that's why I said maybe you write that, maybe you don't. It depends on what you're comfortable with. But now we look at the left-hand side. And if we want to come up with this, MATLAB's got a function that's built in for something like that, right? If I want to take the product of some terms, the function for that in MATLAB is product. And then I'd say, well, what would I like the product to be? I would like to take every single a sub I here, and I would like to raise it to its stoichiometric coefficient. And so that's what I write inside of my product. I would say a. Now I do need the element-wise operator because I am dealing with two vectors, right? So I'd say take the product of all of the a sub I, and raise them to their stoichiometric coefficients. And so that piece of code looks very similar to the code as though we would read it in the book, right? This little bit of code here looks very, very similar to the way that we would actually write the thing, which is this, right? Those two look very similar. Left-hand side refers to the left-hand side of equation 2.30. Yeah, left-hand side is the product term in equation 2.30. And then we would have to ask ourselves, is the left-hand side equal to K sub A? Maybe it is, maybe it isn't. If we wanted to write it in root finding form, we could do so. But this is a good approach that calculates everything the way that we need it to in its most sort of natural form. So if I try this in Matlab, we can actually very quickly demonstrate what fsolve is doing. So here we are over in Matlab. So if I just pick a value of squiggle, let's just say it's 0.25, and then I write all of my parameters the same way that I did a moment ago, 3, 1, and 0, n is equal to n0 plus nu times psi, y is equal to n divided by the sum of n, and then we'll just skip and say the left-hand side is the product of A raised to nu. The target, if we wanted to do that, would say something like, how about output is equal to left-hand side minus Ka. So we can also define Ka as, what was the Ka that we had? 43.97. Right, so this is equation 2.30 in root finding form. And so we can set this up to just display the output a few times. And now we can demonstrate exactly what fsolve is doing. So this, let's see, lecture 7 sample. If we run this code, oh, I forgot an A. Where is my A? Oh, yeah, this should be Y. Thank you, Matlab. So I calculated this and I got my output as minus 43.5, but it should be 0, right? If I've got my output in root finding form, I will have solved this problem when I guess a particular value of xi or squiggle that results in the output being equal to 0. So it's definitely not 0.25. If we try 0.5, we got a little bit closer, try 0.7. Okay, so it's somewhere between 0.5 and 0.7. Try 0.6. Minus 27, not quite high enough. How about 0.65? Better. How about 6.6? Even better. 6.7, 6.8. There we go, right? It's somewhere in between 0.67 and 0.68. And we did that just by guessing xi over and over and over again. And that's exactly what fsolve is doing. And so we can actually take this sort of a script that we've got set up here and modify it for use in fsolve. The way that we would go about doing that is we no longer guess xi, right? We're going to let fsolve do all of the guessing. And so we're going to turn this into our local function. Right? So we do exactly the same thing, right? Within the local function, the input is the extent of reaction, but we don't know what it is, right? We're letting fsolve do all of the guessing. Where do we want fsolve to start its guessing? We could start off with 0.25. And now instead of me typing in more and more numbers and figuring out when is the output actually equal to 0, that's what fsolve does, right? So we say the solution is given by fsolve. What do you want me to optimize? I want you to guess values of xi until my function is solved. And I want you to start at my guess, which is xi sub guess. This approach is exactly the same thing as what I was just doing, except we've now let Matlab do all of the guessing and checking. And so if we run something like this, we find out, yep, sure enough, the result was somewhere in between 0.67 and 0.68. But Matlab has found that solution to a much higher level of precision than we ever could just by guessing numbers over and over and over again. Is the guess and check form for root finding? Yes, ultimately the guess and check only works for root finding, but there are different ways that you could put it in if you don't like this particular form. How could I graph the function to get an initial guess? For this one, I would have to do a for loop if I wanted to graph this, but that's a good question, right? How did I know to guess 0.25, right? It could have been anything between that and the inlet one. And so in order to plot something like this particular function, I would have to generate lots and lots of values for xi and then plot them all. So if I wanted to do something like that, I have not vectorized my function, so it probably would not work if I passed it a vector. And so this particular approach, for anybody that's interested in it, is actually in your book. It is in section 1.4. So if you want to duplicate what I'm about to do right now, see section 1.4. So I would just populate xi with a guess from, say, I don't know, 0.25 to 2, right? I'm just throwing out 100 different values. And then I want to figure out the root. This is called pre-allocation, and then I'm going to use a for loop. So I'm going to say loop over all of the elements of xi, and then calculate in each one the response as my function of xi of I. Right, so this little for loop that I've set up right here, that's the same thing as what we were just doing, where we're just picking lots and lots of values of xi and figuring out what the root happens to be. The root needs to be 0 in the way that I've written it, but the for loop is just another way of doing exactly that. And then I would plot it this way. And so once my plot comes up, I think I have made a typo somewhere. Xi's got it, root's got it. Let me look at my root and see what's wrong in here. Roots are all 0. I'm just tracking down a mistake right here. Ah, yes, I is equal to 1 to the length of I, not just the last element. Thank you, Max. There we go. Let's dock this. So here's my plot. Evidently, something goes wrong around 1, so there's a not a singularity, a divide by 0 happening in there. So I'm just going to zoom in on the lower side. Actually, let's just cut it and say, let's only go up to 0.9. There we go. If we replot that and zoom in on my root here, we can see that it crosses somewhere around here. Right, so if I draw a horizontal line over from 0, right about here is where it crosses through 0, and that's right around where I expected it, right, about 0.667. So if I needed to plot it, that's how I would go about plotting it. I can use the same function to plot it. Once I have that, so this would give me an initial guess of like 0.65, something like that, and then I could use my fsolve in the same way that I did before. But if I just wanted to solve it, that would be this particular portion. So this type of formulation that I've got down here in my local function, that can save you a lot of time in terms of algebraic mistakes, because you're allowing Matlab to do a lot of that algebra for you. For example, in this step, you're calculating all of those outlet molar flow rates. And in this step, you're calculating all of the mass fraction or mole fractions. And similarly here, all of the products of those activity terms. And so you can get around doing some of that algebra in a step like that. So cool, we are spot on time. It's 2:46. We're going to take a break until 3 o'clock. I will leave this code up for now. I am going to go put on some hot water and we are going to have a little bit of fika. So take your time, go grab something to drink, get up, stretch, do whatever you want to do. I'll keep an eye on chat, but I'm going to mute my mic and share a little bit of that music from earlier, and then we'll pick things up again at 3 o'clock. So let's turn on the same one we had a moment ago. Ooh, I don't like that one. That one's too upbeat. I like upbeat music, but not that upbeat. Ooh, there, we had that one. Sneaky Snitch. That's the one we were actually listening to earlier. So that, we'll turn it down a little bit. Cool, there we go. Okay, I'm gonna mute my mic. I'm gonna make myself some tea. Feel free to shoot me a question in chat if you need me to answer anything. Jay, to your question, how do we know if there's a limiting reactant in the first place? There are some rigorous ways that we can go about that from CENG 100, but normally it'll be, we're not going to be dealing with systems that are a little bit more physically reasonable, so there will be one that's kind of obvious to be the limiting reactant, and it'll typically be the more expensive one. But if you need a rigorous way to do that, you can pop open your 100 book, and there are just ways to find out, well, if I use up all of this material, will I have any of the other one left? Will it go negative or not? And if so, then the other one's the limiting reactant. But for the most part, the examples we'll have, it'll be fairly obvious. Like one will be pushed in at, like, 100 times the flow rate of the other one or something like that. You're welcome. Thanks for that question about the quiz. I still have not gone through and updated the one problem that I know has a mistake in it, so they'll all be updated. It's kind of a long process, so it might be like tomorrow afternoon, something like that, by the time the quiz scores are updated. There was a question in chat about how to solve or how to plot problem 1.6. And so that is going to form something like a for loop. You're going to need that. And so the solution for plotting that looks like figure out how to solve that for one value of temperature, and then set up a for loop to solve lots and lots and lots of values of temperature. If you're having trouble getting the for loop working, you can also copy paste your code and do probably like, I don't know, 5 or 6 of them manually and just change the temperature manually. But ultimately that one, or not ultimately, the intent of that one was to use a for loop in the way that it's described in section 1.4 in the book. And you can couple that with section 1.7 to pass in the temperature each time so that the equation is solved for different temperatures each time. Sure. Like I mentioned at the beginning of class, I've got myself a little peppermint tea here. And some very good coconut cookies. Surprisingly good coconut cookies. And they're perfect size for fika too. They're very tiny. But I did get 2 of them. You can email me and ask me to confirm a value for homework, but just be ready if I might end up responding and saying like, no, I'm going to let you figure that one out. most of the time when I want to give you an answer, I will have already done so in the project or in the problem statement. But you can always ask. The worst thing that happens is to say, I'm not going to answer that. Anybody out and about that can still hear me? I'm thinking about another 2-3 minutes and we'll get started. Ooh, that's some good tea. I like that peppermint tea. All right, turn down the sneaky snitch. We're gonna get started again. Pause that. And let's see. Let's make sure. Right screen is sharing. Yep, should be okay. Pause one other thing in the background. And There we go. All right. So we are leaving our realm of equilibrium, at least for a day, for the next 40 minutes or 50 minutes, something like that. John will come back to equilibrium a little bit to tie it into the other thing that we're going to talk about today, which is rate law. This is one of the areas where if you had me do one of your Triton Day presentations when you were still just a wee little chemical engineer before you got into our program, I would have mentioned that chemical engineers are not chemists. We rely on chemists to tell us the chemistry. This is a great example of how we are not chemists. We do not take a very deep dive into rate laws. We assume that the rate laws are generally given to us. If you come back to us for your master's degree, or really if you go anywhere for your master's degree, the graduate level reaction engineering will focus a little bit more on rates, but even then it doesn't go into the depth that most chemistry courses will. In fact, we kind of take a left-hand turn at graduate school and talk more about a specific type of a rate law. And so what we're going to do today is just sort of summarize the usual patterns that we see for rate laws. They're mostly, they're not really something that becomes a particular issue when solving a problem. They're sort of an aside, sort of like the way that we calculated the shortcut equilibrium coefficient, right? K sub SC. It'll get to the point where that just becomes sort of like one part that we do when we're working through a problem, and it becomes kind of routine to calculate that over and over and over again. Similarly, we're not going to go into a lot of depth with the rate laws. It's just going to be a part of the problem that we kind of write down at the beginning. It's not like we're going to be solving rate laws for unknowns or something like that. So the general form of the rate laws that we deal with, they're all going to be abbreviated with the letter R. And we're going to see different subscripts, and the subscripts are going to be indicative of what kind of rate we're talking about. The general rate R, that has no subscript on it, has a set of units, and units are denoted by the equals sign with a dot above it. So this means has units of. And so this general R has units of mole reacted. It could be kilomole, it could be millimole or micromole or whatever, but it's always an amount. It could be pound mole if somebody's being difficult. Per unit volume, per unit time. This unit, the mole reacted, that's a weird unit. It's the same unit that we saw when we were dealing with extensive reaction. It's the same thing. It's the same type of unit. It's referring to how many times has that particular reaction occurred per unit volume, per unit time. There is an equivalent version. We're not going to do a lot of homework problems like this, but it will be on the project. The whole project is based in this set of units, which is mass reacted per unit volume, per unit time. Virtually none of the approach changes in terms of dealing with the reactants, or sorry, dealing with the rate laws, except the stoichiometric coefficients are usually funky. And so this is the set that you'll use on the project, but you'll see they work very, very similarly to everything else that we're dealing with. The reason that that's used on the project is because your project is based in the bioengineering world, and bioengineering tends to favor the mass units because it's often very difficult to define a molecular structure of, for example, a cell. You can't just write a closed form molecular formula for a cell. If we have multiple reactions, we will have one R per reaction, the same way that we would have one squiggle per reaction, one R per reaction. So for example, where we used to have squiggle 1 for reaction 1, this is going to be more often seen as the R for reaction 1. We used to have squiggle for reaction 2. We still do. It's not that it went anywhere, but more often we will be using the rate of reaction 2, and we call that R sub 2. We can go all the way up to squiggle sub J, which is the rate for reaction J, right? And so those are the rates for each one of those, and we get 1 per reaction. For each one of those reactions, the rates of species rates, are related to the R with no subscript by the stoichiometric coefficients. And this is a form you may have seen in chemistry. So the plain old R, the rate of the reaction, is related to the species rates as given by a subscript with a letter, divided by the stoichiometric coefficient for that particular species in that particular reaction. Similarly, you would have R sub B divided by nu sub B, all the way up through whichever species you have, which in our book is written as R sub all the way up to species Z, or compound Z, although you are not limited by any means to 26 components. Not at all. The subscript that's Z on here implies a different set of units. This now is moles of Z, either generated or formed. We don't really specify whether or not it's generated or formed per unit volume, per unit time. Right, so if you see a rate with a subscript that's got a letter, that's referring to a particular species. If you see a rate with a subscript that's got a number, that's referring to a particular reaction, and the two are related by this particular form, right? So the value here, if this is an R sub J, it's referring to a particular reaction number. If it's an R sub A, like we've got here, it's referring to a particular rate of a particular species. And they're related just by their stoichiometric coefficients. And we're going to play around with this for quite a bit. Shouldn't it be generated or, oh yeah, thank you. Generated or formed means exactly the same thing. It should be generated or consumed. So it doesn't matter if we're making something or destroying it. Thank you. Generated or consumed. There is no difference between generated and formed. I just misspoke. Thank you for pointing that out. And we're going to practice this here in a minute. So don't worry if this is coming at you a little bit fast. When we see a couple of examples, I think you'll pick up the pattern pretty quickly. For the most part in this class, we're going to be dealing with what are called elementary reactions. We're going to deal with a lot of non-elementary reactions as well, but those are actually easier in some senses for a reason that I'll get to in a minute. And let's just say that we've got some arbitrary reaction A plus B goes to C plus D. And the lower cases are the stoichiometric coefficients. So the lowercase a and the lowercase b and the lowercase c and d are the stoichiometric coefficients for those species. And then the uppercase ones like uppercase a, uppercase b, etc. Those are the actual species that we're interested in. So anytime that we want to examine an elementary reaction, we can write what is called the elementary rate law, or elementary rate, it's referred to interchangeably, is going to be an R. It can actually come in two ways, so give two columns here because we're going to look at two of them. Usually it's R is equal to some constant that we call a rate constant, which is a K. And then there's two different ways that you can represent a concentration in most cases. One way is a concentration of A and a concentration of B, which is Ca and Cb, and then raised to their stoichiometric coefficients, little a and little b. That's probably one of the more common ways to do it. This is valid if you have a gas or a liquid. We can write it this way. And the concentration that we're dealing with, NEC sub I, is the moles of I per unit volume. Again, it could be like a kilomole or a millimole or a micromole or whatever, but it's generally a mole per volume. The other option that we will encounter is you can write the rate is equal to some rate constant K, and now instead of the concentrations raised to their stoichiometric coefficients, we can write a partial pressure raised to their stoichiometric coefficients, P sub A to the A, and P sub B to the B. This one is only good for gases. But a lot of gas phase reaction rate laws are written in terms of partial pressures because it's very easy to measure. And so here, the P sub I that we're dealing with is the partial pressure defined as Y sub I times P. So this is the same partial pressure that you would have dealt with in 102. How do you know which one is which? Something's got to be told in the problem statement to tell you to pick the P's or pick the C's. They are not equivalent. And so if you're given everything in terms of, for example, the partial pressures, there's not a convenient way to go over and switch your rate law into concentrations. It can be done, but you generally should not do it. If it's a liquid, then you have to use the concentrations because we don't have another option for something like that. And again, we're going to practice writing a few of these in a few minutes, so bear with me here. The K that's written here is called a rate constant. And so the rate constant is immediately difficult to figure out which one you are talking about because it looks really similar to the equilibrium constant. Believe it or not, I'm trying to write that as a lowercase k. So the rate constants are always lowercase. And the equilibrium constant k sub a, equilibrium constant k sub a is always supposed to be uppercase. But as you can tell, my two letters look virtually identical. And so the best way to tell those apart is either A, from context, so you'll be able to tell just from context which one we're talking about, or all of the equilibrium coefficients will always have subscripts like k sub a or k sub 0, k sub 1, or k sub something else. And so you'll be able to keep track of them that way. They'll always have, well, except for 0 or 1. The subscripts on the other k are usually 1 per reaction. And so the subscripts that you'll see on something like that will be numbered like a reaction would be. And so you'll have to do your best to keep track of, in terms of context, which K should I be talking about? Am I talking about a rate constant K, or am I talking about an equilibrium K? And in, sorry, John has the far harder problem in his Friday lecture because he will use them both in the same equation. So he'll have to figure out a way to remind you which one is which. But it's supposed to be a lowercase k for a rate constant. And these always follow the Arrhenius form that you probably saw in chemistry, which is a times the exponential of E sub a over RT. And just a bit of nomenclature here. This, we are so clever with how we name things. The factor that shows up in front of the exponential is called the pre-exponential factor. Isn't that great? I love it. E sub a here is your activation energy. R is your usual gas constant, and T is your absolute temperature. Right, and that's about as far as we go into that. That's what I mean when I say we are not chemists. If a chemist were here, that would be the stuff they're interested in, right? How do I know what the activation energy is? How do I find the pre-exponential factor from, quantum mechanics and statistical mechanics? We don't care, right? If for all of our cases, those will be given to us. Should E sub a be negative or positive? It will generally be given to you as a positive value. And then if I double check, all of this, or sorry, the activation energy is all in section 3.4. Oh, I see what you mean. Yeah, there's supposed to be a negative sign here. Activation energy is usually given as a positive number, but there's a negative sign inside of the expression. I think maybe that's what the question in chat was about. E sub a itself is a positive value, but yes, I did forget a negative sign in there. The units on K can vary. And they specifically vary with the way that the reaction is written. Oh, another question in chat. Is there a table for constants or activation energies? Not really. Usually those are the source of entire publications is just to give you rate constants of particular reactions. Occasionally, you can find a book that summarizes a few common ones, but they're very tricky to come by, which is why they're just going to be given to you in this particular class. Let's say, for example, we had the reaction A goes to B, and we chose to write this elementary rate in terms of concentrations. That rate law would look like R is equal to K times Ca. And if we wanted to know the units on K, the units on R are going to be mole per volume per time. And those have to, remember dimensional consistency from CENG 100, those have to have the same units as K times the molar concentration, C sub A, which is always going to be moles per volume. What's the A in the equation? A is just called a pre-exponential factor. It's a constant. It'll be given to you. Right, and if I rearrange this, I'll find that K has units of 1 over time. On the other hand, by the way, in that particular expression, we're being a little bit sloppy with the moles on either side, but that's okay for right now. Similarly, or I should say, in contrast, what if we write it in terms of partial pressure? Well, the units on the rate are still going to be the same. They will always look like some kind of a mole per unit volume per unit time. And that still has to match the moles on the other side, but the moles of the partial, or the units of the partial pressure are going to be units of pressure, right? So things like atmospheres or PSI or kPa, something like that. And so for this particular reaction, K is going to have a weird set of units of mole per volume per time per unit pressure. Neither one of those are wrong, and there's not really a way to guess, right? If you are given a particular reaction and a particular rate law, or you're told, you know, this particular reaction, say this one, follows an elementary rate law in terms of concentration, then you just have to use it the way that it's given. And so you can't be messing around with stoichiometry. You can't be rewriting your equations, because if you do, you're going to mess up all of the units, all of the fundamental scaling behavior of your rate law is going to be changed. And so for this reason, among others, don't change the stoichiometry if it's given to you. You will get a fundamentally different rate with different units on everything if, for example, I wanted to rewrite that reaction as 2A goes to 2B. The elementary rate law for this would be A, K, Ca squared. That's entirely different, right? The power dependence of this one was to the 1, and the power dependence here is to the 2. Those are entirely separate. So if you are given the expression, the reaction, you have to use it in the stoichiometry as given if you're going to worry about rates. That's a separate matter from when we were talking about equilibrium, right? Equilibrium doesn't care what the stoichiometry is as long as you're consistent through the whole calculation. But the rates, it very much does. And the reason for that is because the elementary rate law, when you write it down, depends on those stoichiometric coefficients. So you can't just be in there throwing stuff around. It'll mess everything up if you do that. Which is kind of an easy thing to remember, right? If somebody gives you the reaction, use it the way that it's written. If they don't give you the reaction and they still give you a rate, then you're going to have to be careful and figure out what the appropriate form is. There's a question in chat. The rate only depends on the reactants and not the products for today. That's John's topic on Friday is reversible reactions. So everything that I'm writing here is for an irreversible reaction, which only depends on the concentration of the reactants. But we will look at reversible reactions on Friday. Another way that you can calculate K, I was trying to decide if I want to go over this or not, because it's very similar to something else that we saw before. But since any old k is equal to a times the exponential of minus EA over RT. We can do a trick not unlike the trick that we did with relating two equilibrium coefficients, equilibrium constants, to relate two rate constants. So since we have that particular form, we can take the ratio of any two k's at two different temperatures and get a form that looks very, very familiar to us. Exponential of E sub A over R, 1 divided by T1 minus 1 divided by T2. Right, so in the same way that we could adjust an equilibrium constant if we knew what its value was at one temperature, we could adjust it to another temperature fairly easily with a form that looks like this. We can do the same thing with rate constants because they follow a very similar form. And so this particular form in your book is equation 3.10. And you should compare it to equation 2.e. I can't see my number on my book, 2.29. And you will see that they are virtually identical. In fact, the primary change is just, am I using an E sub A here or a delta H? And so it's just a convenient form to have. And you can practice adjusting rate constants in exactly the same way that you would adjust an equilibrium constant. I promise we're getting to examples. I know we're just throwing a bunch of rules at you right now, but this is the very last rule. If more than one reaction, what we're going to be very interested in is, well, actually, we're only going to be half interested in this, half interested in the other one. The net rate of species I is equal to, first of all, we call it the letter R sub I, right? So whenever you see the letter R sub I, the subscript is like a letter referring to one of the species. This is what we call the net rate of species I. And in fact, that occurs whether or not you're dealing with one or more reactions. But it particularly comes up with multi-reaction systems. If you want to know the net rate of I, you sum up all of the rates of I in each one of the individual reactions. And so if we write that in math, what that looks like is the sum over all of the reactions. So there's up to Q reactions of the stoichiometric coefficient times the rate for that particular reaction. This is a really helpful, I'm going to do one of those. Oh, that's a lot of coloring. Give me a second here. This is going to take a minute to color in. This is one of the very useful, it looks fairly simple the way that it's written here, but when it actually comes time to apply it, it can take a little bit of work to apply it, but it's a very useful expression. You can use it whether or not there's multiple reactions or not. There tends to be no reason to use it for a single reaction, but you still can. There's nothing wrong with something like that. But we're going to use that particular reaction quite a bit. So let's take, can I see an example of the values for new IJ? Yeah, so we're going to spend the rest of class. We've got like another 15 minutes or so. We're just going to look at examples of various multi-reaction systems. So examples. We can practice actually writing all of these with a single multi-reaction system. Let's say that in a particular system, we have, what's the Q above the sigma? Q says run up to all Q reactions. Right, so that could mean J is equal to 1, J is equal to 2, J is equal to 3, all the way up to J is equal to Q. It's just the abbreviation we say for the last reaction. So let's say we've got a system that has two reactions. The first reaction is 2A goes to B plus C. And all of these are, we're going to assume they're elementary. And the second reaction will be A plus C goes to D. This is not an uncommon form for a set of reactions. So this first reaction, reaction 1 up here, that's probably the one that you want. So for example, you're trying to make B or you're trying to make C, and then reaction 2 is probably unwanted, right? Because you're getting a little bit of your product is recombining with your reactant and you're producing something you didn't want, which is D. And so forms like this are pretty common. This reaction we would refer to as J is equal to 1, and this reaction is J is equal to 2, right? That's the reaction that we have. The Q for this is 2. The reason Q is 2 is because we have 2 total reactions. The rates of each reaction, right? So if these are elementary and we're going to write them in terms of concentration, the rate of reaction 1, so we subscript it with a 1 because we're talking about reaction 1, the rate of reaction 1 is equal to the rate constant of reaction 1, so it's K with a subscript 1, times the concentration of A squared. So we know it's the concentration of A because we've only got one species, which is A, and we raise it to the power of 2 because the stoichiometric coefficient on A is 2. So we raise it to 2. Similarly, the rate for reaction 2 is denoted as R sub 2, rate constant of 2 times C sub A times C sub B, or sorry, C sub C. Again, the subscripts here, the A and the C, are coming because we have reactants A and reactants C, and the powers up here, which are basically just left off, they're 1s. That's because the stoichiometric coefficients on both of those are 1. And so we've got our rates here. We could have equally written these, although we are opting not to do so, as R is equal to K1 times the partial pressure of A squared, and R2 as K sub 2 times the partial pressure of A times the partial pressure of C. We have opted not to do that. Those are not equivalent writings of the rate law. The Ks are not going to be the same. And so it's not like you just have a free choice to write either way. There has to be something in the problem that's telling you, do I write this in terms of C or do I write this in terms of P? One way that can come across is they will just tell you, right? They will say, write the rate law in terms of concentration. That means write it in terms of C. They may say, write the rate law in terms of partial pressure. That means write it in terms of partial pressure P. But if we wanted to write them in terms of partial pressure, it would look like what we've got there in the red. Are we assuming the reactants are gases? This is good for only gases. So if you ever write a rate law in terms of partial pressures, that is only good for gases. This one we have not specified. This one could be gases or liquid. We have not specified. Concentration will work for either one of those. And we're not going to specify anywhere in this particular problem. It's not necessary yet. The form won't change depending on which one is which. Actually, let's try and leave that here for as long as I can so that I can write some rate laws. Actually, I think if I can force my writing program to give me a little bit of extra room here and then erase them. Haha, I tricked it. So smart. So how would we write the net rates? So if we wanted to write a net rate, what we're referring to is this particular form, right? So how do I write a net rate for all of those species, A, B, C, and D, according to this particular formula when I'm given these reaction rates and the stoichiometry that's given next to it? The way that we go about doing that is to apply this formula in a couple of steps. The first thing we'll do is just write it, and then we'll expand this particular formula, and then we'll substitute in values from the actual reactions. What do I got? Black. Let's switch over to this one. So the net rate of A is R sub A. By definition, the net rate of A, and you can always write this regardless of whether you have one reaction or multiples, is the stoichiometric coefficient of A in reaction J times the rate of reaction J. And we're going to sum that up. In this case, J is going to be from 1 to 2. Why did I say 1 to 2? I said 1 to 2 because our Q value here is 2, and that's the same as what shows up in the top of the sum. The next thing, what that means, if we write that sum out, is stoichiometric coefficient of A in 1 times R1 plus stoichiometric coefficient of A in 2 times R2. Now we substitute in our stoichiometric coefficients. So the stoichiometric coefficient of A in reaction 1 is 2. That's a big fat arrow that I'm trying to draw up there. Right, so we'll have a 2 for this one. The stoichiometric coefficient of A in reaction 2 is this one. So it's going to be a -1. Let's get rid of my highlighting. So we will have a -2 times R1 plus a -1 times R2. Now we can go ahead and substitute in the rates that we wrote. So this value of R is referring to this value of R. So we just write in what that rate is. And similarly, this value of R is referring to this expression for R over here. Substitute both of those in. Let's get rid of our writing there. And so what we end up with, I'll write it over here. We're going to need a little bit more room here. R sub A is equal to -2 times K1 CA squared minus K2 times CA times CC. The concentration terms here, the CA and the CC, those are not specific to a particular reaction, right? Picture a giant reactor in front of you that's just a big pot. There are multiple reactions happening all throughout that giant pot, but there's only one concentration for species A throughout that whole pot. And so species A, or any species concentration, doesn't get a subscript that's related to a reaction because it's not specific to that reaction, right? It's that concentration everywhere. If we wanted to write the net rate, so I should just specify net rate of A is what we just wrote. This is the net rate of A. If we wanted to write the net rate of B, that's R sub B. The sum looks similar. It's still going to be a sum from J is 1 to 2, except now the stoichiometric coefficients are that of B in reaction J times the rate of reaction J, nu sub B1 R1 plus nu sub B2 R2. And if we combine a couple of steps here, the stoichiometric coefficient, I'm just going to write these right above it. Stoichiometric coefficient, that's a mouthful, of B in reaction 1 is a +1. Let's try to make that a little bit bigger, +1. The stoichiometric coefficient of B in reaction 2 is a 0, right? Nowhere in this reaction does B occur, and therefore the stoichiometric coefficient of B in reaction 2 is 0 because it doesn't occur in the second reaction, I mean. Right, and then we can substitute in our rates as we did before. And so this ends up looking just like a 1 times K1 CA squared. And so this is our net rate of species B. Similarly, we can write R sub C. You can probably get the trend about now, but I always start off with this particular expression to remind myself everything that I'm trying to accomplish here. J is equal to 1 to 2. Nu sub C1 times R1 plus nu sub C2 times R2. And if I look at the stoichiometric coefficients here, I'm just going to have to kind of remember them. For reaction 1, the stoichiometric coefficient on C is -1, because there's a -1 here, or sorry, +1, and a -1 over here on reaction 2. So I just kind of have to keep those in my mind since I can't show everything on the same page, although I do have this written down nearby. So this will be K1 CA squared minus K2, concentration of A, concentration of C. And we'll just write the last one. I'll leave this for you to check on me. K2 CACC is the net rate for D, right? The net rate for D, it can't appear It can't have any dependence on the rate of reaction 1 because it doesn't take place in reaction 1. So it can only depend on reaction 2. And so these are all of our net rates of A, B, C, and D. Net rate A, net rate B, net rate C, net rate D. And so this sort of an example is one that I hope shows you all of the interconnections. It can never get, I want to say, let's see, I hate ever saying something is easy, right? It's never easy the first time you're trying it. It's usually never easy if you're picking it up. Like you probably may have seen this back in chemistry, and it may have been easy by the time you were done with chemistry, but it may not be easy now. I guess what I'm trying to say is all of the complexity of net rates are captured in this particular equation, right? The one that's highlighted there in yellow. It cannot get more complicated than applying this particular reaction over and over and over again. But it can get kind of complicated doing that, right? It's not that it's straightforward to do this in the sense that there can be many, many terms involved in the net rates, but it is, you can always come back to this particular equation and write out a net rate starting from this particular reaction. There's no other form that we will ever do. This is the only one that we've got. So what I would encourage you to do is every time you write out a net rate on the homework, or anytime you write a rate, even if there's only one reaction, start from this equation and see if you can write the net rate out because it's going to pay dividends big time because throughout the entire course we have to write these net rates and they're going to look like this a lot. That's the only form that we've got, so you'll have to get used to it. So we've still got about 10 minutes left in class. Let's see, is there anything else that I wanted to point out over here? Oh, one comment about whether or not something is elementary or not. If it doesn't follow this form, right? If something is not an elementary reaction, that's, I think I had alluded to it earlier. If it's not elementary, we call this non-elementary because we are super clever in how we phrase things, and R must be given. Right, so if you see the word non-elementary anywhere in a rate or in a problem, look around because the rate has to be given to you. You cannot guess the form of a non-elementary rate law. It doesn't. There's no pattern for a non-elementary rate law. The only patterns that we have are for elementary rate laws. So in that sense, it's excuse me, somewhat easy in a sense that a non-elementary rate law just has to be given to you. And so non-elementary rate laws are things that involve like fractional powers, or there might be fractions written inside of there. They're very, very common in the bio regime. And so when you look at the project that I'll post later this afternoon, all of those rates are non-elementary, but don't let the word non-elementary scare you. They're dealt with in exactly the same way. It's just slightly, ever so slightly easier because somebody gave you the rate law, right? You don't have to guess that, oh, maybe this is an elementary rate and I need to write the rate. No, a non-elementary rate is just given to you. And so you can use it exactly as given. So that was, I think, the only other comment that I wanted on here. I guess we can do another quick couple of examples. Feel free to ask me a question in chat because I'm just going to do another example of a net rate calculation, and I'm going to be bringing this up. Oh, that's a good question. What does it mean to be elementary? It's kind of a circular definition. An elementary reaction is one that follows an elementary rate law. And an elementary rate law is one where you have these, oops, it's supposed to be a highlighter, where you have these terms, the concentrations raised to their powers. That's what an elementary rate law means. They come up most often when we're looking at what's called a reaction mechanism. And so if you want to know what a reaction mechanism is, that's described in your book on section 3.5. And so 3.5 says, well, where do elementary reactions come up most often? Elementary reactions are usually the ones that we use to build up an actual mechanism. So it's very rare, for example, if I write an equation like this. Oops. If I write my equation like this, it is highly unlikely that that reaction actually happens by a molecule of A colliding with a molecule of C and combining to give you molecule D. There are subsets of reactions that actually do occur that way, but more often it's, A hits something and it loses an electron and becomes an excited species, or one of the bonds moves a little bit and it gains a little bit of energy and it reacts with something else and reacts with something else. And so there is a very important subset of reactions that really are elementary, but they're usually steps in a mechanism. And that's covered in a little bit in the book. It's covered more in either a chemistry course or a graduate level reaction engineering course. But for the most part, we'll just specify that a reaction occurs in an elementary form. And what that means to us is when we want to write the rate, it follows this particular pattern. And that's about as far into an elementary rate as we get. Does any reaction that looks like A plus B goes to C plus D elementary? No, it's got nothing to do with the form of the reaction. We can have very bizarre looking reactions that are still well approximated by elementary rate laws, and we're going to investigate some of those towards the end of class. Is there ever a time where an elementary reaction can't be solved with the elementary rate law? That's kind of a contradiction in terms. If something is called an elementary reaction, it is called that because it follows an elementary rate law. And so if it doesn't follow an elementary rate law, we don't call it an elementary reaction. If a half a mole of A was reacting with B, do we still have, for the elementary rate law, A is a half and B is 1, or is it automatically non-elementary? It depends on the way that it is written. So, for example, if we had the reaction 1/2 A plus B goes to C, we can write an elementary rate law for that. Right? If I wanted to write an elementary rate law for that, let's just assume that it's in terms of concentrations. We would write K sub Ca to the 1/2 and C sub B to the 1. That is an elementary rate. Oh, I'm sorry. I think maybe the question was, do the powers change? The powers are always positive in here, right? So you take this 1/2 and you put it up here in the power as a plus. You don't switch its sign. If I doubled the stoichiometry on this one and said A plus 2B goes to 2C, I can also write an elementary rate law for that as R is equal to K Ca times Cb squared. But these two are not the same. Right, this one is not equal to that one. And that actually is, it's nice that we came up to this point because there's a question, or there's a boxed comment in the book that I can reiterate here. All rate laws must be verified, or generally they're actually found in the first place, or found experimentally. There are a couple of tricks that we can use for very basic reactions in like quantum mechanics and stuff like that, that we can estimate what the actual rate law is. But this sort of begs the question, right? I am definitely allowed to write the equation like this or like this. Nothing is stopping me from doing that. But how do I know whether I write it like this or I write the rate law like this? Lacking an experiment, you cannot tell. There is no way to know which is the one that actually represents the real system. You have to do an experiment. We avoid that by just giving you the rate law and saying this is the one that it follows. Can I give you an example of a non-elementary rate? Sure. Non-elementary could be, for this one, something like R is equal to a capital K times Ca divided by 1 plus a lowercase k Ca. That would be non-elementary. That is actually a very common form for bioreactions, and you'll see it on the project. And there's no way to guess this form, right? I could never tell you, enough information that would result in you happening to guess the correct form of that. So that's an example of a non-elementary rate. Would the activation energy differ with the stoichiometric coefficient? Yes and no. So that's part of the reason that I wrote here that all rate laws have to be verified experimentally or just found in the first place experimentally, because we have no way to know what the appropriate form is here or here. We could write either one, right? We could just change the stoichiometry and rewrite the rate law and get completely different results if we rewrite the rate law, both of which would have, essentially different activation energies. We have no way to know which one is true in the sense of which one represents an experiment until we actually do the experiment. And that's not something we get to until the very last part of class, not today, like the last week of class. We have to be able to do an experiment to figure out which one is the actual form. Can you do the projects in groups? No, everybody needs to do their own project. But like the homework, if you want to work together because you have questions and you are sort of working together in that sense, yes, you can do that. But every project has to be done individually. Yeah, working together to do things like troubleshoot code can be really great because it's very, very rare that two people get the same interpretation of code, that they use all the same variables and things like that. So A, it's really easy for us to check if you're just emailing your code around because the forms of those never match up. But B, it's a really good check on two people to compare two different sets of code and say, I know we got to get the same answer here. Maybe somebody's getting it and somebody's not. Or personally, I think the best case in terms of learning is if you've both got two different sets of code and you're both getting the wrong answer, you can both learn so much from your thought processes by trying to troubleshoot the other one's code and getting them to agree to the correct answer. So I'm all about working together in terms of solving individual portions of the project, right? Troubleshooting code and things like that. But like it would be in a homework, ultimately you all have to do your own work. So you can't just be sending off code to everybody else and having them submit the code on their own. And that actually brings us to 3:50. So I want to make sure that I don't go over time in terms of generating any new content or anything like that. But I can also hang out for a few more minutes and answer questions. So I'm just going to click on the music to remind everybody that lecture is formally over. I'm not going to introduce anything new, but if you have any questions or anything, I will stick around and chat and try to answer as many as I can. Thanks all. Stay safe out there. Good luck with the homework, and we will see you on Friday. John handles reversible rates. Question in chat about how to approach problem 1.7. Let me just share the screen. 1.7 is as faculty member, we tend to, or as instructors, we tend to say like, yeah, that's a good problem or that's a bad problem. That's a good problem, but what I mean by that is like, usually that translates to that's a tricky problem. So on problem 1.7, it's got the 3 diamonds because it is tricky. And so what you'll end up having to do is write an expression for squiggle extent of reaction for this reaction and another expression for the extent of reaction for this reaction. And so you'll have a system of 2 equations with 2 unknowns. And those 2 unknowns will be xi1 and xi2, or squiggle 1 and squiggle 2. And so then you'll have to solve those. There's an example of how to solve systems of reactions with fsolve in section 1.8 in your book. And so you'll have to set those up to solve them simultaneously. Once you get the squiggle values, then what I would suggest, or the extensive reaction, the way to actually check it against the value that was given in the problem statement is to use a table kind of like this one. Right? Once you have your squiggle for both reactions, you can calculate the outlet molar flow rates of all of the components, and then from that you can calculate the outlet mole fractions of each one. A good approach for that one too is this part that I was describing earlier today, because you can save yourself a lot of writing if you do, or sorry, not a lot of writing, a lot of algebra if you try to use an approach like this. But ultimately you can write it to get an expression that looks like this. Where'd my pen go? So you can end up with two expressions that look like this one. One for one reaction, one for the other reaction, with 2 separate KD sub A's and 2 separate extensive reactions, and solve those simultaneously. Either approach works, right? Either figuring out these 2 equations or using this Matlab approach works. I mean, both of them you'll eventually need Matlab, but depends on how much algebra you want to do and how familiar you are with vector notation in Matlab. questions have slowed down, so I'm going to give it about another 2 minutes. How do you pick a guess for two values of squiggle? Pick them to be small numbers. If you have it as set up in this particular form, this one, right? If you have two of those, you can plot those two and look for places where they intersect. But those tend to be surface plots because you have two variables, and so they look more like an intersection between planes, which is a little bit harder. And so instead, you just kind of pick some small values based on whatever the inlet molar flow rate happens to be. So if the inlet molar flow rate is 1 mole for that problem, maybe you pick a squiggle of about 0.1, 0.2, something like that. Nothing really hard. Yeah, you can plot it. It looks like a surface plot if you try to plot it. So it can be more effort than it's worth to just create a surface plot. You're welcome. Us to about 4 o'clock, so I'm going to wrap it up. I'm going to stop the recording here. Lecture notes will be posted afterwards, as will the recording itself. As soon as Zoom finishes processing, we will get the recording posted. Thanks all, good luck, stay safe out there, and we will see you on Friday. Okay, let's turn off some music. Stop our record.